Okay, so I think we are ready to start with the afternoon session. So our next lecturer will be Herman Verlinde from Princeton University. His course will be on double-scale SYK and de Sitter holography. And please, once again, remember to wait for the microphone for the questions so that everybody can hear. Thanks.
Okay. First, I want to thank the organizers for, again, inviting me to give these lectures. Trieste is a special place for me. I went to one of the first, maybe even the first school when it received the new name, the School of Superstring Theory. And for me, the school here has had definitely an impact on my development as a string theorist, and later sort of as someone who started thinking about other questions. So today, I'll be talking about the connection between this model, which is called the double-scaled SYK model. It's a soluble model in quantum many-body system in one dimensions. But the real interest for me is that it has a structure that indicates that, in my mind, at least from one of the first examples of a system that really has a great promise to be a dual to de Sitter gravity. Many of you are familiar with ADS-CFT, and it would clearly be an important step if we can move away from a negatively curved space and start learning something about de Sitter space. The subject is sort of definitely still new, and it's still being developed. At the same time, there's already enough results and work in the area connected to this story that it will not be possible for me to give a complete overview even in the next sort of 4 lectures. So please, again, interrupt in case you would want me to explain it a little bit more. I'll give a little bit of hints of various places where you can read more, but I'm around here the whole week, most of it, and you certainly should take the opportunity to ask questions both during the lecture and after, outside the lectures. So the overview, at least of my 4 lectures, will be today, indeed, since I don't want to assume that everyone knows immediately how holography works, I'll have to give you some introduction and some motivation. I'll do that today. So today will be mostly sort of review, sort of to set the stage. Then I'll discuss the double-scaled SYK model in tomorrow morning's lecture, how to actually do computations and actually to show how you can solve it. And then hopefully you start seeing structures emerging from the solution of the SYK model that you can start recognize. And indeed, in the 3rd lecture, I'll discuss, perhaps surprisingly, because the SYK model is in 1 dimensions, it turns out that the connection is really with 3-dimensional quantum gravity. So I'll discuss 3-dimensional quantum gravity, and in particular the one that's relevant for de Sitter space in the 3rd lecture. And then in the 4th lecture, it's even sort of a more surprising connection where I'll connect it with what's called Schur indices in supersymmetric gauge theory. But by that time, we're already much farther along. So let me just get started. So for today, again, I'll talk about holography. And most of you know the motivation for holography. And of course, the main motivation is the famous formula for the entropy of a black hole, or actually also for the entropy of de Sitter space, in particular Hawking and Gibbons for the case of de Sitter space, and Bekenstein and Hawking for the case of a black hole, identified the area of the black hole horizon divided by 4 G Newton as the entropy of a black hole. And in the de Sitter space, as we'll discuss shortly, there's also an horizon, and the same formula has been proposed for the de Sitter space. And of course, the fact that entropy is proportional to the area, again, indicates something slightly unusual. Normally, entropy is extensive, and that led at Hooft to sort of introduce something that we now call the holographic principle. And ADS-CFT is sort of our main example of realization of that. And it would be enormously exciting if something like that, and it can be done for de Sitter space. One of the lessons, of course, and one of the goals, essentially, of holography is precisely to develop a description of, say, cosmology. So for black holes and in cosmology, you can start talking about entropy, which kind of introduces the motivation, or at least the ambition, that one wants to be able to introduce a Hilbert space description or quantum mechanical description of these systems. And then, although, again, this entropy could be interpreted in many different ways, one of the ways in which one would hope to interpret it is that e to the s which could potentially be a function that might depend also on energy, for example, the mass of the black hole, or if we start introducing energy in the context of cosmology. But this should be the dimension of the Hilbert space as a function of energy. Or if you wish more generally, you can call this rho of E, and then it becomes the spectral density, where this entropy counts the number of states. So if you're able to count the number of states, then you can keep track of quantum information. And both in the case of black holes and in the case of cosmology, there's something that you can call the black hole, or the quantum information paradox. So that's called the black hole information paradox. In the case of black holes, it has to do with the fact that it's hard to sort of imagine how a black hole can have a temperature, because indeed, I should of course mention that if there's temperature, then from that there's also a corresponding, so if there's entropy, there's a corresponding temperature, such that the temperature times the change in the entropy is the change in the energy. So of course there's the first law of thermodynamics. And if you have a thermal object and it can, in the case of a black hole, evaporate, indeed the question is, how does quantum information, how is it preserved if you can have a thermal state potentially as your final state if you had started with an initial state? In the case of cosmology, for me there's always been another kind of information paradox, because in cosmology, and in particular in de Sitter space, space can expand. And that's basically the hallmark of a cosmology, certainly of the cosmology that's relevant to our universe. And if space expands, again, regardless of whether entropy is proportional to the area or whether it's proportional to volume, typically, at least you might assume, that certainly from the point of view of low energy effective field theory, that the number of degrees of freedom that you have access to will increase in time. Nonetheless, if quantum information is preserved, which is one of the principles that we would like to impose, then it becomes a puzzle how one can make a theory of quantum de Sitter, a quantum theory of de Sitter space, such that quantum information is preserved. So indeed, there are paradoxes that one would like to be able to resolve. So this is certainly sufficient motivation to be looking for a system that would potentially give you a quantum description of holography. Finally, I should say another important sort of motivation, of course, is that, again, ADS-CFT is an example. We kind of know nowadays that it's possible to start with a quantum system. So quantum mechanics is going to be our postulate. And in this case, it's going to be this SYK system. But then what emerges from that is a system, an effective description of the system that looks like a theory that has gravity in it. So the idea is precisely that if the spectrum of a theory is finite, in the sense that this number is finite, then there are already arguments that if you have the first law of thermodynamics satisfied, and also if you take ADS-CFT seriously, then gravity is not something that you put in, but then it becomes emergent. So this is, of course, a pretty ambitious program, is to have examples of this. And one of the reasons for sort of looking at simpler models is that many of these questions are not dimension specific. Again, the black hole information paradox, sort of the tension between preserving quantum information and an expanding universe, and also the notion that gravity is an emergent phenomenon, are all not dimension specific. So if there are examples where we can sort of make these things much more concrete in less than 3 dimensions, it's clearly the place that we would like to start. So this is sort of my summary of the motivation, and then I'll get started on essentially giving you a lightning overview of how holography works in lower dimensions. Unless there are questions or comments at this point. So this is my motivation. Yes?
Usually when one considers holography, one thinks of gravity, fluctuating gravity, and a theory of QFT with infinite continuous degrees of freedom. Here you are using double-scale SYK, which is a quantum mechanical model. So that means that de Sitter is somewhat special in...
Right, right. You're getting ahead a little bit. So the different notions of sort of finiteness. It's true that in the context of ADS-CFT, that the dual system sort of has an infinite number of degrees of freedom. One way of truncating the system, which I'll describe just in like 2 minutes, is indeed still to put the boundary, say, on a cylinder or in a finite volume, and then fix the energy range. So for a given energy range, there's still a finite number of states. But you're correct that there's, and we'll see that happening, is that there's really a qualitative difference between anti-de Sitter space and de Sitter space, in the sense that in de Sitter space, literally there's going to be a bound on this thing. And indeed, so de Sitter space by itself doesn't give you the freedom to keep raising the energy and having an arbitrary number of states. That's right. Are there other questions? Okay. So let's start with ADS3 CFT2. Let me erase this one here, give myself a bit more space. So this is a very actively studied sort of example of the ADS CFT duality. 3-dimensional anti-de Sitter space. One way of writing the metric is as follows, is that if this is a radial coordinate, and suppose that I work in Euclidean space for now, and my boundary is parameterized by Z and Z bar, then the ADS metric looks like that in units where the ADS radius, curvature radius is 1. And then one way of thinking about it is indeed sort of to do some coordinate mapping where the boundary, say, lives on a cylinder. And then the y direction is the perpendicular direction here. The CFT lives on the boundary, and the bulk here is ADS. Now this would be great, and of course some of it immediately kind of almost follows from the fact that the symmetries of anti-de Sitter space and the symmetry of a 2-dimensional conformal field theory actually matches. The isometries of the Sitter space is the conformal group in 2 dimensions. But stuff really gets more interesting, and this is actually where the formula that I erased is important, namely that if you go to finite temperature, so we heat up the CFT. Again, the reason why holography immediately is going to sort of do something interesting in ADS space is that what you're going to get in the middle will no longer look like EDS space, but essentially you're going to find that there's a black hole solution in the Sitter space. And this black hole is dual to the CFT at finite temperature. And that gives an enormously sort of important sort of hint, or at least confidence, that black holes should be describable by quantum mechanical system, because the boundary is a quantum mechanical system, and if we can make this correspondence, we're in good shape. And what we're mainly going to be learning about this is indeed this picture that I was describing here, that the dimension of the Hilbert space should be finite, and it's useful actually sort of to have a mental picture of this thing. So the entropy of a black hole is usually a pretty big thing, a big number, and therefore this spectral density for energies that are relevant to this situation is actually very large. So the number of states per unit energy is large. If this is E equals 0, then, and maybe I'll say one or two words about it, but again, one of the things you have to know for conformal field theory is I'll be talking about the spectrum of states, but there's a relationship between the spectrum of states and the operators in the theory. So indeed, there are operators associated that create these states, and these are called heavy operators. And then generally, there's going to be some light operators. And those light states or light operators, if I act with the corresponding operator, and that could be a local operator that sits in the boundary, I'm sending a particle into the bulk with a given mass, and indeed for these states, that mass is small. But an important idea already that will play has been playing an organizing role in low-dimensional holography is that most of the interesting questions don't have to do with the specific light states that I get out for a particular conformal field theory. What's interesting is that generally there's a gap for a holographic CFT where the heavy states basically are the black hole states, and the light states are just individual particles. But what's important is that the physics of the black hole states are not specific to the particular CFT that I'm going to be looking at. So this heavy spectrum of black hole states is universal, because indeed the black hole solution in the gravity theory has universal properties. So we can deduce universal properties of this spectrum from the point of view of the ADS-CFT correspondence. But the same is true actually from the point of view of the boundary, and I'll explain that in the next 20 minutes or so, because the logic behind all of this is relatively important for what follows. Also from the point of view of the CFT, you can understand why this structure here is universal. Okay. And the logic there indeed makes use of sort of the special properties of CFTs. Let me first write down actually the black hole metric. So there's a black hole in 2+1 dimensions, which is the BTC black hole. And the metric indeed looks like this. It sort of looks like a typical black hole metric. So here I'm going to a Lorentzian signature. And for simplicity, although the BTZ black hole could also be a rotating black hole, to keep my formulas a little bit simpler, I'm assuming a non-rotating black hole. Then the BTZ black hole metric basically looks like that. And then the relationship between R plus squared and the mass of the black hole is that this is, I'll call the mass of the black hole energy. So M is mass, is E. And I think there's a -1 here. So that's the formula for R plus. And if you plug that in here, you find a black hole solution. Locally, and this is one of the reasons for why low-dimensional gravity is sort of a soluble theory, is that if you take the Einstein equations in 3 dimensions, if there's no matter source anywhere, then locally the metric is just a constant negative curvature space. So locally the metric actually kind of looks like that all the time. However, again, this R plus parameter has some non-trivial sort of effect on the global geometry, and indeed it essentially leads to this presence of this black hole that sits in the bulk. Vertically is time, I should have mentioned that here. And then the spatial slice is a 2-sphere, or at least a disk, if you wish, in the bulk. And it's surrounded by a circle, by an S1. So there's something topologically non-trivial about having a black hole in this space-time. And indeed, it means that if you go around this black hole metric, locally, again, it looks like entity zeta space, but after returning, after 2 pi, you basically find that your coordinate system has changed. And precisely, the coordinate system has changed by means of an isometry of the space-time. And therefore, this thing kind of indeed is a non-trivial solution. And this isometry that specifies the black hole is parameterized by this R plus. But now let's indeed do our math. The simple math is we can now immediately determine the entropy of this black hole by using indeed this formula. I should mention this formula, I would say, has now taken on the form of a postulate. Some people say, hey, are you a string theorist? Are you doing string theory? Nowadays, I think most string theorists take the following point of view, and this is, I think, a point of view that any person who's studying quantum gravity should take, is that I think there's no distinction between all the approaches to quantum gravity if we agree on the following principles, is that let's assume that this formula is true. There's a lot of evidence for it. So this is going to be one of our postulates. So here's the list of postulates, basically. This formula should be true. Quantum information should be preserved. And physics should be compatible with locality in the bulk. At least if that an observer who lives in this space-time should experience this as a semi-classical space-time. If you take those 3 principles and you can give a quantum description of a space-time or based on those 3 principles, you've basically solved the problem. I didn't tell you that, by the way, that I should have gravity in the system, but it kind of is sort of almost a consequence, but let's make that also maybe on our wish list. But those are the principles. So therefore, indeed, a prediction that the gravity makes, which we have to, and then confirm with the CFT, is that the entropy is 2 pi times R plus. And I should tell you that indeed that's the size of the horizon, because R equals R plus is the horizon. So this is the circumference of the horizon divided by 4 g Newton. So these formulas will combine, specify as a function of the energy. And for large enough energy, if 8 g Newton n is large enough, then basically what we find is that this is 2 pi times the square root of 8 g Newton E divided by 4 g Newton. So here's already an important statement, is that the entropy, indeed, of this 2-dimensional CFT, at least, or the gravity theory as a function of energy should behave like this. In the case of a 2D CFT, by the way, this gap here indeed is basically due to this -1. So it turns out that the energy needs to be bigger than a certain value before you actually have a black hole. But I couldn't draw it here, but this keeps going to infinity. So in 2-dimensional CFT, as we just discussed, there's a finite entropy as a function of energy. But if I draw it as a function of energy. Indeed, it's a square root, but it just keeps going. And E goes to infinity on here, so this direction is E. As we'll see in a second, this behavior is quite different in the case of de Sitter space, and this is one of the reasons why it's going to be very interesting to be looking for a dual description of de Sitter space. In two-dimensional CFT, this is indeed the behavior, as I'll explain in a second. Are there questions about this? This is maybe as much as I want to say about the BTC black hole, because I'm going to have an analogy, a partner here, and this is going to be Schwarzschild de Sitter. And it might be interesting to already start comparing the two. But unless there are questions here, then let me sort of move on to the Schwarzschild case. Okay. Again, I'll make the link with CFT in a second, but let me first talk about what happens in de Sitter space. So de Sitter space, let's initially forget about the Schwarzschild. Let's just talk about de Sitter space itself. De Sitter space looks like this. And if this is in 2 + 1 dimensions, then in 2 + 1 dimensions, de Sitter space can be viewed as in terms of embedding coordinates as the following equation. I take basically 4-dimensional Minkowski space, and I put this combination equal to 1. This is, again, a Lorentzian space-time. But now, indeed, this direction, so this is what's called in an embedding space. I could write down a metric, but this is actually my favorite way of thinking about de Sitter space. There's going to be some special place, at least if I look at it this way, where the circumference has a minimal size. But then if time moves up, the space expands. I'll be talking more about de Sitter space tomorrow and in the third lecture, but I just want to write down the metric. And the de Sitter space metric, again, you can always choose different coordinates. Let me, in this case, write it as follows. Pure de Sitter space looks like this. So this is pure de Sitter space with radius 1. You can already see a bit of a similarity between this metric and that metric. Notice that the r squared is here to the left of the r plus squared. And if I want to turn this in Schwarzschild de Sitter space, indeed what I'm going to do this thing. It turns out that this is Schwarzschild de Sitter. So the special case r plus equals 1 corresponds to ordinary de Sitter. But when r plus is not equal to 1, and in general r plus will be less than 1, and it turns out that the equation for r plus in relation to the energy of the Schwarzschild de Sitter solution is very similar to that one, but the sign is reversed. So this is a Schwarzschild de Sitter solution. Again, now this is now a solution with positive cosmological constant. There are questions. I'll talk more about the solution in a second, but let's indeed take some questions here.
Just a small question. In both cases, in BT zeta and de Sitter, phi is a compact coordinate?
Phi?
Yes.
Yes. Thank you. That's a very good question, because phi will play an important role in a second.
Yeah,
So phi is indeed in between 0 and 2 pi, whatever. And same thing here.
and also, okay, there that BT zeta, you are taking already a limit without rotation, right?
So here, indeed, I wrote down indeed the BTC without rotation. That's
So
right.
we are like in another, like, I don't know if it's a, like more heavy plot part of the spectrum, or it's like a limit like more radical than seeing the spectrum that you have behind. I mean, it's like since we're working, yes, with BT zeta, where the angular momentum goes to 0. If we are, yes, that part, even more, okay.
Yeah, so but it's true. I could include angular momentum in this story, but the formulas just get a little bit more complicated. Yeah. In a moment, actually, probably I will include angular momentum as a possibility. Also, in this case, it is possible to include angular momentum, but again, it introduces new subtleties. But okay. Yeah. One up there.
In the ADS-BTZ case, the energy of the black hole should be bigger than some number.
Correct.
And in the Zeta case, energy should be smaller than some
Correct.
value.
Okay, you're anticipating an important point, yes.
And there is a physical explanation.
Yeah, so as you can see, just the sign flip has immediate consequences, indeed, for the range of energies. And it's not surprising. I didn't draw you so one of the important points is that, again, this was in the Euclidean coordinates. Time is actually one of the boundary coordinates. And this y coordinate is indeed a spatial direction. So the boundary is the part where the space-time becomes infinitely big, the ADS space-time. Here I can write down the analog for the de Sitter metric. That would be ds squared, and let me call that coordinate eta, the eta squared minus plus, say, dz squared, dz bar, divided by eta squared. So in this case, the analog of this y coordinate, this, by the way, is the static patch coordinate. This by the way, this would be what we call the global de Sitter spacetime. This coordinate system only describes one patch of this sorry, not static. This is the expanding patch. But this is one way of thinking about de Sitter spacetime. But now, indeed, it's the eta coordinate which actually plays the role of time. So the boundary of the de Sitter space sits in the past and in the future. But that means that any spatial section of the de Sitter space is finite. And the fact that volume is finite, whereas in this case, every spatial section actually has infinite volume in the bulk. So this is why it's going to be possible to put an infinite amount of energy in anti-de Sitter space, but it's not possible to put an infinite amount of energy in de Sitter space.
Energy in de Sitter is quite hard to define in global de Sitter. You only have it for the static patch,
Correct.
And it will be the energy that the observer measures, right?
Correct.
Here, the energy you are associating with the mass of the black hole.
Yeah, excellent question. For now, the fact that I'm calling it E here is simply because of the analogy with that formula. And indeed, there's a certain notion, certain sense in which this is the energy of the state. But you're correct. In this case, indeed, there's what we call a boundary stress tensor that allows me to actually measure this energy sort of asymptotically. You can do the same thing here, but then you have to kind of use this asymptotic region to define what you mean by the stress energy. And then you do get this number.
Right.
So it is possible to give that sort of same definition. But again, it's more subtle because it's now.
Okay, so for now, this energy is not necessarily the one that the observer on the static patch would measure.
Right. You're already starting to talk about the observer. I'm going to be talking about the holographic screens in a second.
Okay.
Right now, I'm just making a statement about the geometry. And in 3D gravity with positive cosmological constant, this is a solution.
Okay, thank you.
Another question here.
Yes, since I'm not familiar with this geometry, where is the black hole?
Good question. I'll talk more about it. Yeah, three more questions.
Probably exactly that question. So R is positive, right? The coordinate R is positive. So I guess it naively looks like this has only one horizon. But then if I think of a Schwarzschild black hole sitting in de Sitter, there's the cosmological horizon as well as the black hole horizon. So
yeah, maybe before I get 3 times the same question. This thing is called, okay, there's a typo. Schwarzschild de Sitter, just to confuse all of you. So the Schwarzschild name is there because this thing looks like the Schwarzschild metric, doesn't it? It kind of does. But it turns out, indeed, that it's not a black hole.
Yeah, okay. I guess it's a similar question in that the BTZ black hole you have written is, I mean, it has Schwarzschild black hole has a single zero on the horizon, whereas this has a double zero, which is like an extremal black hole, extremal BTZ.
Yeah, yeah, I should have maybe done a few more things before I wrote down this metric, but I think at least I provoked some questions by writing down the metric. This thing, by the way, it's not a black hole. It does have a horizon. Namely, it has a de Sitter horizon, which I'll talk about in a second. But indeed, yeah, so the interest of this space-time is not so much that in this case we want to study what black hole horizons do, but we want to start studying what cosmological horizons do. That's the interest of this space-time.
Maybe a stupid question. There seems to be an upper bound on E,
Correct.
but there doesn't seem to be a lower bound. It feels like I can make E arbitrarily negative.
Okay, you're radical. I always assumed that I'm interested in space-times because I was about to write down this sign here. And I think I'm going to kind of assume that energy is going to be positive.
Okay.
And I'll tell you in a second why I'm doing that.
Okay.
But so I don't want to have negative energy. I'll tell you a bit later because the argument is going to be that I can write down the same formula over there. And in the end, I want to have the de Sitter spacetime to be the spacetime with maximal entropy, the pure de Sitter spacetime. Yeah. So arc is 1 is the de Sitter spacetime.
Maybe relatedly, the range of coordinates for the BTZ black hole is that R goes from R plus to infinity, and I guess for the Schwarzschild that R goes from 0 to R plus?
Correct. So this is the metric in what we call the static coordinates. The actual, I should probably draw the panels, the diagrams, which I can do over here. So indeed, we're only looking at the patch outside of the horizon. So let's draw the 2 spacetimes here. So BTZ, I guess the way I'd like to draw it, this Penrose diagram is sort of more like this. If you do the global BTZ, then it's actually a 2-sided geometry. Looks like that. This is then the boundary. This is where the boundary, the CFT lives. And then that coordinate system lives over here. And this is R equals R plus. And then 2 pi R plus is the BTC black hole. And so and this here is R to infinity. So R equals infinity sits over here. Okay. Now, let's draw the Schwarzschild de Sitter Penrose diagram. So pure de Sitter spacetime looks like this. Where now actually, yeah, so this boundary up here is where the eta goes to 0. That sits up here. So this is scribe plus, I guess. This is future infinity. So where here it's the black hole horizon, the black hole singularity. Here this line is future infinity. This line here is actually R equals 0. And this line here is still R equals R plus. So now that coordinate system gives me this patch here. So it's not really the boundary, but the boundary of the Penrose diagram, if you wish, is the origin of that coordinate system. So it's just a line, a world line. Whereas here the boundary is a full two-dimensional space. Okay. From this diagram, it's already clear, and maybe I should mention this then indeed, is where is the holographic screen? Because there are kind of two natural choices. If I look at this, this is the holographic screen. That's where the CFT sits. This is what we call the holographic screen. And indeed, what I mean by the holographic screen is where, at least if I have a dual quantum system, I would like to have at least some kind of dictionary where the dual quantum system lives. It's not necessary. The dictionary could simply be some kind of mapping between a quantum system and this geometry. But if I do indeed observations, then I could either indeed make those observations here from the point of view of the boundary of the spacetime, which sits over here. That would be the analog of sitting here, indeed at the boundary of this spacetime, but then I've rotated this thing and interchanged space and time. However, if I think about it indeed as I want to go to the boundary of the spatial direction, then to some extent this world line might be the natural place to put my holographic screen. The nice thing about putting it here is that gravity is not dynamical anymore once you get to the boundary, although I'll make some remarks about that in my third lecture. But the nice thing, at least about sort of thinking about this thing as also the time in the dual quantum system, is that I can start making a dictionary between the Hilbert space of the gravity theory and the Hilbert space of the dual system. So I leave this question mark for now, and we'll talk more about how we're going to think about this. But that's certainly one of the conceptual questions that we have to answer. Another conceptual question is what was discussed is that energy is now going to be bounded. Let's also talk about entropy for a second. So the entropy, again, has the same formula as I had before. Is 2 pi r plus divided by 4g Newton. And this is going to be less or equal than 2 pi over 4g Newton. Because r plus is bounded by 1. 2 pi over 4g Newton indeed is the area of the r equals r plus boundary, which indeed is going to be the horizon. But the reason for why this thing is a horizon is different, a little bit different than in this case. This is the horizon of a black hole, and it's indeed true if I send in a signal, and if it keeps going here, then whatever I do here can no longer communicate with the outside. So this region cannot communicate with the boundary. The same is true for this region. if I'm here in a de Sitter space, I cannot communicate with the observer. So this location, this special location r equals r plus, is indeed a special location for the observer that sits at the origin. And again, in our universe, our universe, we think it's expanding. So stuff far away is moving away from us. There's going to be a distance away from us where the stuff that's moving away from us goes with the speed of light. Anything that's beyond that point goes faster away from us than the speed of light. And we cannot reach that point in terms of communication. So indeed, there's going to be a cosmological horizon in the Sitter space because of the expansion of the universe. This thing here, by the way, is called the static patch. And the static patch indeed covers half of the Sitter space at an early moment in time. But then if you look much later, then the static patch is just a tiny patch of an expanding universe. Homework. Think about this diagram and visualize the Sitter space. This is a school, so there should be homework. Okay, now comes another important point. As some people already immediately noticed, this thing doesn't look like a black hole because there's indeed only one horizon. So what makes that space-time different than pure de Sitter space? And the only thing that space-time actually contains that's different from pure de Sitter space, turns out, is that this line r equals 0, that is actually the point where the matter sits in that geometry. So,
question?
This space-time actually has at the origin, somewhere at some special location, it has a conical singularity. So this is a pure de Sitter space, but with a conical singularity. And the way to do that, to see that a bit more explicitly, unless there are questions, I'm going to do this trick again. I hate it when people sort of use the eraser with equations, but I'm going to use the eraser one more time.
I have a question.
Yes.
Here. So you are so when we usually consider Schwarzschild de Sitter like this, the coordinate range is taken to be between the radial coordinate between minus r plus and plus r plus, where the minus r plus is taken as the black hole horizon. So you are probably truncating your coordinate range to be r at r equals 0, I guess.
Yeah, r equals 0 for me is a special. So what you're probably talking about is that if I would not have this part of the metric.
Yeah, for DS2, for instance.
For DS2, then r could go between minus r plus and plus r plus. But the minus part is sort of the other part of the circle. If I already have the circle, I can restrict my r to be positive. And then just rotating by 180 degrees is the same as flipping the sign of r.
Okay, thank you.
Yeah.
Just a very quick clarification on like the coordinates you wrote on the right side of the blackboard. Like, do you intend those to be the so-called inflationary patch that is like half of the Sitter?
Yeah, so those coordinates that I have over there, the eta coordinates, they cover all this triangle.
Yeah, okay.
The eta so those coordinates on the right, the expanding patch covers this whole triangle.
Yeah, so when you say that like the Sitter has somehow a finite volume to distribute energy in, you're thinking of the global coordinate patch. Because in a way, looking at that, if I think of a spatial slice in that coordinate system, I would say that it has infinite volume.
At any given eta?
Well, eta is fixed to go to
right. So it's true that in that coordinate system, I could in principle, but indeed, a fixed eta slice looks like this. And indeed, that fixed eta slice reaches this point here, and that's indeed why it has infinite volume. So it's a good question. So indeed, if my time evolution goes like this is the time evolution of the metric that's all the way on the right.
Yes.
And those slices indeed are infinite. But the notion of energy is most naturally defined in a metric that's static. So if I take a static perspective, then I can talk about conserved energy. In this case, the space-time is time dependent because it's expanding. And indeed, yeah, right, energy in that aspect is not literally conserved. Right.
Okay, thanks. But this also begs the question then, like, is there a clear representation of this Schwarzschild de Sitter space-time in the inflationary patch, like when it comes to auto?
It's a good question, which we can discuss after my second lecture.
Thank you.
Okay, good. Because indeed, that's right. There are many interesting questions that immediately pop up. By the way, I think when you start thinking about de Sitter holography, one of the reasons many people, at least certainly I, have wanted to start thinking about de Sitter space for a long time, but every time I ran up into a barrier, that the number of questions started exceeding the number of answers that I could think of. And I think we've reached a tipping point where I think there are more answers sort of popping up over time. So we kind of are a bit farther. I may want to sort of move on a little bit, although the questions are great, last questions, but yeah.
So if this is not a black hole solution, why do we assign that entropy? Like if it...
Why do we... I'll give an answer to that in a second, okay? So R equals R plus in this case is still the place where the horizon sits, but it's the cosmological horizon. So the observer that sits here, if I again go to my static patch coordinates, the static patch coordinates indeed cover only this right triangle. So for this observer, the horizon is set by R equals R plus.
So Herman, just to, so this is not the Narai black space-time, right? So it's really de Sitter, not Narai.
It is de Sitter, but still it's a state with different energy than the full de Sitter space-time. It's a space-time with less different entropy than the total de Sitter space-time. So it's a way of studying thermodynamics of de Sitter space. So it's true, as I'll explain again in a second, R equals 0 is the special point. And one thing you can do is to actually rescale R and again absorb this R plus into R. Sorry, I can rescale T and phi in such a way, all combined, so that this R again becomes a 1. But then what will have happened is that phi is no longer between 0 and 2 pi. It's between 0 and 2 pi times R plus. So it turns out that my Schwarzschild de Sitter spacetime actually looks like this. So it just looks like de Sitter everywhere, except that phi is no longer a periodic coordinate with 2 pi, but it's periodic with 2 pi R plus. Okay? So that's a very important point, is that this is an angle, there's a conical deficit angle. So there's a conical singularity. And it's a deficit angle because R is less than 1. It would become an excess if energy would be allowed to be negative. But I'm assuming again that phi, again, is only between 0 and 2 pi times R plus less than 1, which means that de Sitter space, and that's an important lesson, de Sitter, pure de Sitter, is a state with maximum entropy. Another lesson, of course, is that energy and also entropy are bounded. Okay. So if I would make a plot of the de Sitter entropy, let's now erase this over here. So this was for the BTZ black hole. Now, I guess, so this is for the SDS. This is for BTZ. If this is energy and this is entropy, then it actually goes like this, goes like the square root basically this is S of E as a function of energy. So it has a maximum at E equals 0. And then when E is equal to 1 over AG Newton, that's when the entropy is 0, and that's where the conical deficit is actually 2 pi. Okay? So it's a very different behavior. It's actually also useful to do briefly the thermodynamics for the Schwarzschild de Sitter solution. So de Sitter has also a temperature. But it immediately also introduces a slight puzzle. I wrote down this equation. Let me write it for beta, which is 1 over the temperature. It's the S dE. This is, again, the first law of thermodynamics. And if I use this equation, then I'm finding that this thing is minus, you do the math, 2 pi over square root 1 minus 8 G Newton E. I take this formula, I plug in that formula in here, and I differentiate, I get this formula, including that minus sign. So this doesn't mean that the temperature of the Sitter space should be finite, but in some sense I should put a minus sign in this equation here, because what I called E is the localized energy that I have to put to create the conical deficit. But in some sense, maybe I should be interpreting E as something that extracts energy from the Sitter space. It certainly extracts entropy from the Sitter space, because this thing slopes down. If entropy becomes smaller with energy, indeed temperature is negative. But I'm going to put a plus sign, and indeed this is what we believe to be the temperature of the Sitter space-time. I'll call this thing beta Gibbons-Hawking, because Gibbons-Hawking basically proposed this to be the temperature of the Sitter space-time. We'll actually sort of confirm in various ways that this is actually a good definition of temperature. So as you can see, as soon as you start thinking about the Sitter space, there's quite a few sort of puzzles that pop up. Surprisingly, actually, it turns out that one of the funny properties of the SYK model is that the thermodynamics of SYK has many puzzles in it as well. And a lot of the confusions that we're running in here, we'll meet them again when we start thinking about the thermodynamics of SYK. Turns out that SYK also has a maximum entropy state. It also can have negative temperature. And it also has this feature that even though you might be sitting at a point of maximal entropy, nonetheless, indeed, the temperature is finite. And these are all kind of strange features. Okay, how am I doing with time? Where's the clock? Oh, here it is. 15 minutes. Are there more questions? Okay. So let me do a little bit of CFT, just sort of to set the stage for things we have to be doing later. But it was great to have all these questions, because indeed that's like the best preparation once we start talking about the SYK model.
Maybe one question regarding this discussion. So right now we said that you can think about this Schwarzschild de Sitter as a state in the Sitter space-time, even though it only describes like some partial slice of the space or some patch of space.
Correct.
So usually when we think about, I don't know, states, we think of something that covers a whole patch of space. So doesn't it run into all kinds of trouble, specifically on this diagram in the bifurcation point? Or?
Very good. Let me introduce the same trouble over here. So here we feel, this is ADS CFT. In that case, we kind of feel better about it, but only partially. indeed, there's a way of reconstructing the bulk from the CFT, essentially by sending signals in and out. This is called the HKLL construction. But we've had sort of hot debates about how to reconstruct the interior of a black hole. Precisely, it's because it's hard to reconstruct what happens there. So your description, and it's true actually, even in this space-time, if I draw this slice here, then there's a part of the slice that sits inside of the black hole. And even in this case, by the way, this inner patch kind of expands as well. So and many people have made this point, is that even in ADS space, once you have a black hole and you're sitting inside of the black hole, you kind of are a little bit in a cosmological setting where there's a time-dependent spatial geometry. And then indeed, the question is, how do you construct operators here? You have to start having sort of clever discussions about what it means to look beyond the horizon. And that same question pops up here. Even though in this slicing, all the way on the right, it seems as if I can immediately access things over here. But from the point of view of this observer, I have to start doing more clever things. And we'll see those things happening.
So I guess in the BTZ case, one would usually say today that you cannot really construct a good state for this double-sided geometry unless you have a Hilbert space on the left and Hilbert space on the right or something like that?
No, I think the better answer, my preferred answer is that it's sort of a state-dependent protocol. Yeah. So with state-dependent protocol, you can get to here, and the same should be true here. But it's very interesting to study that same question here. Okay, just to introduce very quickly a little bit of technology, because in the end we want to sort of start explaining these formulas. This is sort of our phenomenology, but we'd like to explain these formulas from a dual perspective. So let me very quickly sort of summarize in the last 10 minutes how one would sort of rederive the formula for the entropy of the BTZ black hole. And in principle, we'd like to be able to do the same thing then for the de Sitter spacetime. Yeah, so the CFT that lives on the boundary is a quantum field theory. So it has a stress energy tensor. And it turns out that the stress energy tensor is sort of has already enough structure in it, in a two-dimensional CFT, that you can reconstruct many of the properties of the bulk theory just by thinking about the stress tensor. And it's not surprising because the stress tensor is the operator that couples to the metric. It's defined as the response due to a variation of the metric. In two-dimensional CFT, the stress tensor is chiral conserved, so it can be written as two components, one which only depends on Z, one on Z bar. And then we often expand this thing. If we do radial quantization, which I don't quite have time to explain what it is, but you put it on the complex plane and you look at the Laurent components of the stress tensor, this thing satisfies the Virasoro algebra. So, and this is an infinite dimensional algebra. So it's true that the two-dimensional CFT has actually an infinite set of conserved quantities because, yeah, it's a symmetry algebra, and it has to do indeed just with basically repointizations of the coordinate Z. And indeed, the algebra of reparameterizations is represented by, indeed, this first line of the algebra of the Virasoro algebra. This thing is the central charge, which in the ADS CFT dictionary, I think it is, what is it, 2c over 3 is 1 over g Newton. Again, this is a units where the radius of ADS is equal to 1. So the weakly coupled limit in the gravity theory is the large central charge limit. people often say, okay, hey, two-dimensional CFT, because of this special property that there's an infinite symmetry group, two-dimensional CFT is integrable. And indeed, all the examples of two-dimensional CFTs that we actually know how to solve, indeed, are essentially integrable, and we call them rational conformal field theories. In ADS CFT, we're not interested necessarily in those integrable conformal field theories. We're kind of interested in the most sort of random, non-integrable conformal field theory, where this is literally the only symmetry of the problem. And if the CFT only has Virasoro symmetry, actually we don't have too many examples of that. But indeed, it's still believed that essentially the structure of a CFT is precisely this spectrum that I talked about, where the very dense part of the spectrum is very random and very dense. And therefore, the CFT that I want to be talking about has a property that's analogous to quantum chaos. A quantum chaotic system, and it has a very dense spectrum, but it doesn't have typically any conserved quantities, except for, indeed, for this case, for the Virasoro algebra. What I'm drawing here, this spectrum, is actually the spectrum not of the CFT as a whole, because these LNs have integer labeling and need to increase the energy by an integer. So that's a very regular part of the spectrum. The spectrum that's very random is where you talk about the spectrum of primary operators. So the primary spectrum is random. And a primary state, for most of you, you know it's defined indeed by, say, conformal dimension H. It's annihilated by Ln for n bigger than 0. And L0 on H is then just H times H. And then you can start acting with the L minus n's on this thing, and you get what we call conformal towers. Now, the derivation actually of the formula that I wrote before for S as a function of energy was done famously by Cardy. Nowadays we call this thing the Cardy spectrum. And the Cardy part of the spectrum is, again, precisely this part here, where the entropy is proportional to square root of E. And Cardy indeed derived that the spectrum, I hope I get the formula correct, is C times, by the way, yeah, let me also introduce a thing that I call delta, which is the left moving H plus the right moving H. So it's basically twice the conformal dimension H. And then I always forget if there's a 3 or a something like this, 12 maybe.
What is the ADS dual of, for example, RCFT or something?
What is the ADS? Okay, good question. If you have a CFT with a small central charge, in part because of this formula, it would be an ADS spacetime with a very small curvature radius. If you have a CFT which has many more symmetries than the Virasoro symmetry, a priori, at least one thing that you could have is you could have a current algebra. And the current algebra, presumably, again, should be related to a gauge field. At least we know that if you have a symmetry, there's a gauge field that lives in the bulk. If the symmetry gets really sort of too large, then the thing that breaks up typically is this gap here. So the fact that the theory only has Virasoro symmetry kind of means that there are not too many conserved quantities or at least not too many fields in the bulk. If you do have higher symmetries, typically you're going to get a very irregular spectrum here that becomes like a higher spin theory in the bulk. So the short answer to your question is that the dual to a rational CFT would be a theory in a small radius ADS spacetime or at least a theory with very high, many higher spin symmetries in the bulk. Yes.
Here, the entropy on the CFT is computed as the amount of primary states of that energy, or how is that?
Yeah, so the entropy in the CFT is the number of states. If I give you a little energy window, delta E, that number is small, or let me, if that number is small, this window is small, but you still have many states inside of it. And I'm just counting the number of states within that energy window.
Okay, and that is for rational CFTs, right? Or
this is for irrational CFTs.
For irrational, okay.
So in the end, I'm interested in irrational CFTs. By the way, it turns out that this formula is very good also for rational CFTs, except the spectrum wouldn't look like this. It would have huge degeneracies. So basically, I wouldn't have many states that are all degenerate, and they're spaced in a very regular pattern. But the degeneracies would start growing with energy. Whereas here, I have many states that all have different energy, and each of those states only has one primary field in it. Levels has only one primary field in it. It turns out also that if you look in this part of the spectrum, this part of the spectrum is dominated by the primary fields. It's not dominated by the descendants. Most of the states in the system are actually primary states. And they have a random energy. That's the structure. The fact that I'm talking about this thing is actually, we don't have any examples of CFTs that behave like this, but our assumption is that we can make such systems. Rather than maybe giving more equations, let me conclude actually by giving you my paradigm that I've been sort of already explaining a little bit. So what is the paradigm for low-dimensional holography? It's going to be the following, and this is going to be sort of organizing a little bit what's going to happen over the next few days, is that we're interested in a duality between a quantum gravity system and a dual description. So this is in d dimensions. This here is in d+1 dimensions. Now, the thing that lives in d+1 dimensions is some kind of microscopic string theory, but I'm going to put a question mark behind it. It could be a string theory. It might be something else. Here, there's also a microscopic description. Let me call it a quantum many-body system, or a quantum system. This thing could be a CFT, or indeed, in the rest of the lectures, this could be the SYK model, or it could be something else. And the idea is that there's an exact duality between these two. Of course, the most famous example of this exact duality is N=4 Yang-Mills theory over here, and string theory in ADS5 times S5. Now, why are we so interested in this duality? Is that on this side of the duality, indeed, as I explained, there are black holes, and we don't literally know what string theory really is in terms of a Hilbert space. So the quantum mechanics on this side is not under much control. We kind of know that this system contains gravity, but we don't know how to solve the quantum mechanics. The idea is that this should be an exact duality, but it's hard to control because this theory here is strongly coupled. Now, it turns out that you can actually learn an awful lot about this exact duality by taking one step back and sort of coarse graining a little bit. First of all, why are we interested in this particular theory? Because if we look at larger distances and we look at the way the theory behaves, it is a theory of gravity. So there's a universal sector to these theories that all contain gravities and they contain black holes. Somewhat surprisingly, especially in lower dimensional CFTs, or at least holography, as long as we keep C finite and G Newton finite, this theory here is, of course, still a quantum gravity theory. And it turns out that in 2 + 1 dimensions and also in 1 + 1 dimensions, this quantum gravity theory is actually soluble. So there are soluble quantum gravity theories. Those quantum gravity theories actually have a continuum spectrum. And basically what happens here is that what you're going to do is you're going to basically take an ensemble average of all the theories that have this rough structure of the spectrum, again with the gap. And after basically coarse graining, the universal behavior of what happens in this dense part of the spectrum is captured by that quantum gravity theory. Okay? And the same you can do here. It turns out that this microscopic quantum system, if you look at it carefully enough, you can extract actually an effective description. And let me call this effective description the soft dynamics. In the case of two-dimensional CFTs, the soft mode is essentially this mode. In two-dimensional CFTs, you can do conformal transformations. And the dynamics, there's dynamics associated with the conformal transformations. And that dynamics of the conformal transformations is the soft dynamics of that theory. In ADS CFT, this dynamics is the asymptotic dynamics of ADS. So this system also has asymptotic soft modes. But in lower dimensions, so if this is d equals 3 or d equals 2, the quantum gravity doesn't have any local excitations in the bulk. And it turns out that this soft dynamics that lives in d dimensions is actually exactly dual. There's, again, an exact duality between the soft dynamics that lives on the boundary and the soft dynamics, and the quantum gravity theory that lives here. What's nice about this particular duality is that this is actually turns out to be a weak coupling duality. So in the regime where the G Newton is small, this soft dynamics is also weakly coupled. And it's true that, for example, in the Virasoro algebra, the Virasoro algebra becomes basically semi-classical in the regime where the central charge becomes big. So this is basically the paradigm by which we've been studying holography in low dimensions, that we can kind of make a holographic dictionary between a thing that lives in d dimensions and something that's quantum gravity in the bulk. But by the way, this is loop quantum gravity over here. Because it turns out that you can actually quantize low-dimensional gravity using the methods of loop quantum gravity. But the proper interpretation of what one is doing here is that it's just a coarse-grained or potentially ensemble averaged description of some microscopic theory that lives over here. And here's the same thing, is that basically the soft dynamics can be extracted by ignoring the microscopic details of this theory here and just extracting the sort of generic behavior. So this is a useful paradigm to keep in mind by which we're going to sort of apply that in the next 2 lectures. I think I've used up my time, is that right? Okay, good.
Okay, thank you, Herman, for the beautiful lecture. I think for the sake of time, I will defer further questions to...
Yeah, please feel free to ask questions again at the reception. Why not?
Yeah. But also now we will have a 30 minutes break. So you can ask Herman more questions, and we will reconvene at 3:45.